thank you, everyone, for coming on an afternoon after I'm sure it's been another hard day for many of you. So I hope this will be some enjoyable and interesting input for you. My name is Rob Eastaway, and I was thinking, in these strange times, what would I normally be doing at this time of year? And what I'd be doing, well, what I was doing almost exactly a year ago. March is typically a busy time for us running theatre-based shows called Maths Inspiration. And a year ago, we were at the Reading Hexagon Theatre with an audience of 800 Year 11s and Year 12s mainly. And the idea of these theatre lecture shows is to show students there's more to life than taking exams. So we've kind of moved to doing that kind of thing online, though I'm sure I don't need to tell you that you can never capture quite the same interaction and energy over a video than compared to being there in the flesh. So I can't wait to get back to theatres to be doing that. When I'm not doing talks, either in theatres or in schools or whatever, I fill a lot of the time writing books. And one or two of you might have got one of my books that I've written on my own or with others. I'm really interested in the maths of everyday life and puzzles, and sometimes the two together if they overlap. And so I thought before I get on to my main topic, I would just open with an everyday life puzzle for you and give you a chance to practice the using the poll. If you've seen this before because you've seen a Maths Inspiration show recently, you can vote if you want, but you might want to just sit back and watch other people's votes. But this is a basketball question. I want you to imagine, because you've all seen basketball being played, or you might have played it yourself, but you're viewing the hoop, the basketball hoop, from above and watching the ball pass through it. Which of these four illustrations most accurately shows the ratio of a basketball to the hoop? Is it A, B, C, or D? So I'm going to open up the poll and give you a few seconds to choose which of those you think it was based on what you just saw. So A, B, C, or D. I've been told to give you 45 seconds, so that seems a long time for me to be lingering around, but hopefully you've all found a button. Hopefully you have clicked now, and taking my life in my hands, I am going to, in a second, click through to the results, which are as follows. Okay, so it's interesting. There seems to be the last options seem to be most popular. So D and C. C's just pipped B here, D here with 39 to 34%, followed by B, and A is the one that comes last. That's fairly typical of the results I get in this survey. So let me show you the correct answer, which is A. So well done to 4% of you, and 96% of you just got it wrong, and will be very surprised at this. In fact, so surprised you might be thinking there is something not right here. Why does everyone get this wrong? Or almost everyone. I certainly did when I first saw it. This is something known as the basketball hoop illusion. And there are three reasons I think why people get it wrong. The first one is that sneaky net below the hoop, which when you see the ball squeezing through, it creates the impression the ball must have squeezed through the top as well. So there's that part psychology. Also, the fact that being humans, we assume that because we fail to get the ball through the hoop most of the time, it's because the hoop is very small, rather than because we are actually not necessarily very good at getting balls through hoops. And then the third reason, well, let me just show you the evidence, or the real figures. There's 18 inches for the internal diameter, and 9.5 inches. All sport measurements are imperial, pretty much. So as you can see, tiny bit over halfway. It's a much bigger hoop than you think. And one other reason why we think the hoop is so much smaller than it actually is because we're very hard at judging the size of elevated objects. So it applies to street signs as well. You might go past a sign like that on the motorway and probably think it's about the size of your bedroom wall or something, whereas in fact, it's the height of a house. So I wanted to start with that because I wanted everyone to get something wrong to start with. Almost all of you did. And to recognise no one got hurt. It's actually quite interesting. And it sort of sets me up for my topic, which is the importance of getting things wrong. And one reason why I like this as a slightly provocative title is that I think most teenagers, in fact, most people probably think of maths as the one subject which is all about getting it right. In fact, some people like it because it's the subject where you know you got it right. And I think that can be unhealthy and unhelpful for a variety of reasons. So I really want to just look at things from a different perspective. And this might even be even more resonant now as you've got students coming back into school after so long away. They're feeling even more anxious about getting things wrong. So I'm going to sort of talk about 4 different aspects of getting things wrong. First of all, just to say that, look, mistakes happen. We all make mistakes, and that happens in maths as much as anywhere else, and that's okay. It happens. Also, to just talk a little bit about mistakes being helpful as a part of problem solving. Also, this notion of maths is always right or wrong. There are times when there isn't always a right answer. And I think it's really important for teenagers to realise that is the case, even in maths. And finally, getting it wrong can be interesting, as you just saw with the basketball example. So let me go through these 4 topics, and I'll start with mistakes happening. And when I talk about mistakes and getting it wrong, there's lots of different types of that. There's failure, there's mistakes, there's getting it wrong, lots of different labels we can apply to different situations. But I think almost all of them make us feel bad. We don't like this happening. And 2 examples in maths, well, one is when someone just gets the maths wrong, that kind of mistake. They use a wrong rule or whatever. And I'm going to pair with that the idea of a mental slip. You get it wrong today, even though you got it right yesterday, for example. And these are very different things. Let me give you an example of the wrong maths, which is very close to home because this was my year 10 son doing a probability question last week. What is the probability of picking a red ball and then a blue ball with replacement? So the chance of getting a red ball, 2 out of 6, is 1/3, and the chance of getting a blue ball with replacement, 3 out of 6, is a half. So that much was good. But then the chance of A and B, he added them together rather than multiplying. So that mistake would give a very wrong answer, a very wrong perception of the probability. So it is important to know that thinking is wrong. Compare and contrast that with a mistake, and I'll bring this even closer to home. Now, some of you might have seen or even got a copy of my book, Maths on the Back of an Envelope. If you happen to have the very first edition of the hardback, of which fortunately there weren't that many printed, then if you turn to page 42, you will find this paragraph, tip 5, and at the bottom it proclaims, wrapped around the end of a line, that 430 divided by 2 equals 115. Now, I hope all of you have spotted that is not normally what happens when you divide 430 by 2. You should get 215. How embarrassing in a book with arithmetic in that there should be a mistake. In fact, it's not the only mistake in that edition. In my defence, I didn't spot that, and nor did 20 other people who read the proofs either, including several very numerate adults. But there we are. Mistakes happen, and very painful when you get I probably had 10 or 15 people email me within days of the book coming out saying, there's an error on page 42. There is one redeeming thing, though, which is I think the people who pointed that out to me actually felt quite good. So when someone else gets it wrong, don't we all feel a little bit of, I spotted their mistake, oh, how hopeless they are at maths, all these kind of things. So bizarrely, you getting a mistake, not much good for you, but it can be good for confidence building and smugness of other people. So there we are. Maybe a benefit in making mistakes, if not for yourself, then for others. So as well as those two, a different kind of mistake is this one, blind alleys. Now, I'm going to show you another puzzle. This is a story of a very wealthy magnate called I'm Very Rich, who has a boat that they keep in the Mediterranean in a dock. And it's not tidal, so the water stays at a constant level. But I'm Very Rich has heard that there's going to be a storm, and this is going to buffet the boat around. You can see the rope there is very tight, but of course, if there's wind, the boat might get smashed against the quay. So he sends his right-hand man, whose name is Benolin Chestikov. I hope you like that name. And Benolin, when he gets there, notices that the boat, when the rope is fully tight, is a metre away from the quay. So he thinks, right, what I'll do is pull the rope 1 metre backwards. So Benolin walks backwards by 1 metre. So I have a question for you, and it'll be on a poll in a second, which is, will the boat make it as far as the quay or not? So it's just a yes or a no. So Benolin pulls the rope horizontally by 1 metre, and the boat will, of course, start moving in towards the quay. Does it make it as far as the quay or not? Yes or no? I just want you to use your intuition here, because there probably isn't time for you to work it out. So don't get obsessed with that. And it's your intuition that really intrigues me. So I'm going to put the poll up now. Will the boat reach the quay? Just a very simple yes or no. And hopefully you can answer that quite quickly, because, as I say, I'm not asking you to work this out. I'm asking you to use your intuition first off and see which way that takes you. I'll just give you another few seconds to do that, just to allow the last few people to discover the button. Very hard to judge how long to wait for people to enter a poll. But anyway, I will now click ahead to the results. Okay, 71% of you have voted no, and 28.9% of you have voted yes. So the majority have gone for no. Those of you in the majority are in good company, because when I ask most maths academics this question, they also say no. That's the intuitive answer. Of course, my next question would be, okay, prove it. And if I ask you to prove it, certainly if I ask GCSE students or A-level students or teachers at that level, especially if you've been doing lots of trig recently, the temptation to say, right, I'm going to stick some labels on here. I'm going to call that length of rope L, the height above of the quay above the rope H, and I'm going to put in an angle theta, and I'm going to get myself, it turns out, into an awful mess trying to prove what happens. It's not impossible, but lots of mistakes happen, because as it turns out, and you aren't to know this, that is not the easiest or best way of answering this question, but you kind of need that blind alley almost to discover the elegance of the way of solving it. So let me show you some primary school maths that can help you resolve the question, which is, there's the boat moving in by a distance X, and the rope has shortened. So it was originally L, and it's shortened by a metre, so it's now L minus 1. This forms a triangle, X, L minus 1, and L. And we know the basic rule of a triangle is the two shorter sides have to be at least as long as the longest side. X plus L minus 1 is greater than L. That's just how triangles work. And we can cancel the L's to give X minus 1 is greater than 0, or X is greater than 1. In other words, the boat will not only make it to the quay, if Benolin is strong enough, it'll actually smash against the quay and start scraping upwards, which is very counterintuitive as far as I'm concerned. And I got that wrong. It's one of those surprising little geometry puzzles. But where's the mistake? Well, people have got it wrong, but it's partly because we're applying the wrong model, wrong hypothesis or whatever. But it's a really interesting mistake to make, and makes discovering the right solution very satisfying. By the way, I noticed about 10 minutes before the talk that the "I'm very rich" at the top got inadvertently changed to Abramovich. I think I didn't change an old slide. So there's a genuine mistake on offer. Any connection between "I'm very rich" and people by name of Abramovich is purely coincidental. Please don't tell anyone that I used that name. I'm going to move swiftly on. Okay, so blind alleys, wrong maths, mental slips, other things that can go wrong, trial and error. which is an important part of most problem solving and solving Sudokus. And so, let's try this. No, that doesn't work. Let's try that. Trial and improvement is the other phrase that's used. I like the old-fashioned error thing because it's fine to get it wrong. And then there's being surprised. Well, we'll come back to that later. But I think all of these have benefits. The one that you as teachers probably need to know about to help direct a student in the right direction, particularly, is the wrong maths. But there is value in all of these in some way. So mistakes happen, and some can be very beneficial for others, if not for you. And that is a problem, because the thing about maths is you get better by doing lots of it. But what stops you doing lots of it? Well, one of the major things is the fear of making mistakes. It just stops you trying. And particularly you're going to stop trying if you're afraid you're going to be made fun of, you feel unsafe putting forward an idea because of the reaction of other people. And particularly so if you don't find it interesting. So it's the job of the teacher, I suppose, or the presenter or whatever, whoever's talking about maths, to make it safe to make mistakes and to make the problems interesting enough that your students, your audience, want to have a go. And if they don't want to have a go, you get, I love this word that was given to be a friend of mine, because what you want is volunteers, people putting themselves forward to have a go so that everyone else can see the problem being solved. And if you don't have any volunteers, the word for that is nolunteers. And if you've got a classroom full of nolunteers, alarm bells, you need to find a way of getting around that. And if you don't make a safe environment for mistakes, and you ask someone to do some maths in front of you, then what they adopt is a policy of self-defense. So I'm going to show you one of my favorite examples of this, which is Ed Sheeran, who tends to use mathematical symbols for his albums. Recorded for the BBC. You can find this if you search around on YouTube or the BBC, I think. A little video of him doing a maths test, which he preempts with the statement, "I failed maths and the BBC are going to prove it to you." So a bit of self-defense before he even gets going. So here is Ed Sheeran doing some maths.
Hey, I'm Ed Sheeran. I failed maths and the BBC are going to prove it to you. Square root of 81 is 9. I think 2 cubed is bigger than a quarter of 28. Oof, yeah, smashing it. It's 3.142. Oh, it has to be 180, doesn't it? No, does it? Yeah. Does that, so 45 and 70, so 75.
So close.
How? No, because it... Yeah, no, you're right. £10.80. It's sick. 4 out of 5. Will that be a C or a U?
I'm calling it a B.
B. My girlfriend's cousin, her grade said dude. Not even joking.
Right, so there we are. Ed Sheeran, I failed at maths and the BBC are going to prove it to you, and proceeds to do really well. I mean, that was pretty much grade A standard maths doing in his head. But he's defending himself, as is the natural tendency of people of any level of maths, actually, to cover themselves because this horrible feeling of how other people are going to react to you getting it wrong. And the language of self-defense, we all know it. We all use it, if not in maths, in other things. I'm hopeless at this. You say before you try, or I'm going to get this wrong, or I don't know anything. This is a sort of, I'm not even going to engage. This doesn't matter anyway. Dismiss the problem. And the killer 2-word, who cares? So we all do it. We've got to find a way of managing that. And it can be bright. Children, particularly teenage girls, as a parent of one, nearly two of them. Here's a 15-year-old girl, strong at maths, answering the question, why do you never contribute in lessons? Why do you always stay quiet? The reason why I say nothing is because the others will judge me. That's really painful, but very true for so many. And there's various ways you could think of getting around this, apart from not forcing everyone to divulge their answer in front of the whole class, but doing it in pairs or doing it electronically. I'm sure many of you use that. Or perhaps you could try something like this, the self-defense problem-solving game. If you give a problem which is unfamiliar, you could maybe make it a rule that before anyone puts forward any response, they have to start their response with, I know this sounds stupid, but, or I don't suppose it's, or this is just a wild guess, or it probably isn't this, but. And that way, everyone knows that this is not supposed to be a brilliant answer, and often it is a brilliant answer. So there we are. There's some thoughts on making mistakes and the pain of that and how to get over it. But I just want to build on that by saying mistakes can help problem solving. And I want you to show you a wonderful experiment. Now, here is a puzzle, and some of you will have seen this puzzle before, which is fine. You have a go at it anyway. To remind yourself, there are 9 balls. One of them is 10% heavier than the other 8. And all you have is a pair of balancing scales. And the objective is, in 2 weighings, I want you to identify the heavier ball. So can you come up with a strategy for identifying the heavier ball in 2 weighings? If you already know this one and don't need a second thought to remind yourself of the answer, there is a more advanced version, which I think is in 3 weighings. If you don't know whether the ball is heavier or lighter, what's your strategy? But I'm not going to answer that one. But I will be interested to see how you get on with this. I will go silent for a few seconds just to allow you to think and sketch out. Most of you may not come up with a solution, and it's always interesting to do this when you're working in groups with each other, which is how this experiment was conducted. But I'll just leave you a few moments to consider this. You might also want to imagine how your class would tackle this, what you imagine they would do first, especially if they had a physical set of scales in front of them. Okay, I'm going to. This feels very premature. It's very hard to judge when you can't see a room full of people buzzing and talking and demonstrating. But I'm going to move on to the experiment that was done on a group of adults in Sussex, which found that about 40% of people, as a first attempt in this problem, weigh 4 against 4. This is an efficient way of getting as many balls in as possible. Maybe it's a binary thing, but it's frustrating because if you do that and then 2 again, it's not guaranteed to identify the heavier ball. It might do, but it's not guaranteed to, and we need to find a strategy that will always identify the heavier ball, and it just doesn't work 4 against 4. However, the really interesting thing is what 40% of adults do instead of that. And somebody in the chat has already guessed this. This was Professor Tom Ormerod at University of Sussex found this result. He says that 40% of groups put 4 in one side and 5 in the other. And guess what happens? The 5 goes down. At which point, someone in the group says something along the lines of, oh, that's stupid, isn't it? I've gained no further information because the 5 was always going to be heavier, given that the heavy ball is only a tiny bit heavier than the rest. And you might think, well, that's a waste of time. But here's the kicker. The amazing thing is that on average, what Ormerod found is that the groups where someone starts with 5 against 4 get to the correct solution more often or quicker on average than groups who go 4 against 4. Why is that? It's something to do, he thinks, with The 4 against 4s get locked into a logical, this is a binary thing, and they can't break out of it. Whereas the 5 against 4s, it's a combination of, now one person's done a silly thing, we can all muck in and all ideas are open. And they've broken away from feeling that any one strategy is going to be guaranteed to get there. So I don't know, but I think it's really interesting result. Those of you who haven't come up with the correct result yet, this is the way to do it. I'm sure many of you have spotted this. You put 3 in one side, 3 in the other, and then need a bit of thought maybe, but if, for example, the dish on the right goes down, you know that one of those is the heavier ball. Take any pair of those and weigh them against each other. If they're the same, it's the third one is heavier. If one goes down, that's the heavier one. If this is level, you do the same with the 3 that you haven't used yet. That was a slightly quick and garbled approach, but I'll leave you to mull on that or test it out on the scales at home later on. But the principle is a mistake led to better problem solving. And I actually think that one of the most wise and useful contributions that gets made in problem solving in groups is the person who says, I know this sounds stupid, but so often it's far from stupid. So watch out for people saying that. They're often the wisest people. So, number 3, there isn't always a right answer. There was actually a lovely example on Twitter, or it actually made the press a couple of weeks ago. Some of you might have seen this, but I loved it. It was a question that was actually posed as homework for 8-year-olds, like an 8-year-old. True or false, this shape has 2 right angles. Explain your answer. Now, if we had a poll here, when I don't have a poll here, I'm interested to know which way the majority of you would go. I think perhaps the majority would go with false, but certainly not everyone. I actually thought, this is so interesting. I have an 18-year-old and a 15-year-old at home, and I thought, I'm going to take this down and show them. And there proceeded about 10 minutes of really rigorous debate. I won't call it argument, although some might. But Elder was showing younger, introducing them to the idea of calculus, and in the limit, that is a right angle or whatever. And there was a counter argument for it's always bent. It's not, you can have a right angle between 2 straight lines. I love debate like that about something which is arguable. I mean, we're not going to resolve here whether it is true or false. I believe the primary kids were supposed to come up with the answer false, but I love the idea of being able to debate a problem like that. And it's probably the most engaging, the most engaged I've seen my 2 teenagers on a maths problem for a very long time. That's got to be good news, especially if you can draw some learning out of it. Let me give you another example, though, of right and wrong answers. And this one does have a poll with it. It's a little estimation quiz. So this is Paul Sturgis, who last time I looked was the tallest man in the UK. And this is Dwayne Johnson, otherwise known as The Rock, a photo taken a few years ago. So here's what I would like you to do. I would like you to estimate, maybe scribble down so you can't cheat, how tall is Paul Sturgis and how much does Dwayne Johnson weigh? So put an answer down. Don't put anything in the chat because that will bias other people. And it's very interesting for you to just make your own estimate here. And I'm sure you'll all be dying to know how close you got. Before I show you the correct answer, I am going to write down on this post-it pad what proportion of you have given a particular type of answer. Okay, so I'm going to give you the correct figures here, which, or according to Wikipedia or wherever I got them from at the time. So Paul Sturgis is 7'8" or 232 centimeters. Dwayne Johnson, 18 stone, 8 pounds, 118 kilograms. Well done if you got really close to that. I have a little question for you. which is when you were estimating Paul Sturgis's height, here's a little poll. Did you estimate his height in feet and inches or in meters and centimeters? And I've made a little guess as to what the answer is going to be here. I need to know how close I get to guessing this correctly. But did you estimate in feet and inches or in meters and centimeters as your first instinct? And possibly your only instinct when measuring someone's height. Okay, hopefully that is enough time for you to have picked A or B. Let's see what the results are. Right, feet and inches 61%, meters and centimeters 39%. Okay, I've overestimated you as a crowd. You're much more hip modern than I thought, because I wrote down 80%, which was going to be, can you even see that? 80% is the proportion of you who will go for feet and inches. It was the majority, but not as much of a majority as I typically get from teachers. I mean, isn't it interesting? I didn't do the poll for weight, but I'm going to guess at least a third of you estimated the rock's weight in stones and pounds, probably not in pure pounds, because that's more American. But how imperial we are, given that for 50 years there's been no imperial measurements in school maths, other than occasionally when you're off-piste and comparing them. If you're feeling in any way guilty about that, don't, because the results I get from teenagers are almost exactly the same. In fact, slightly more. I'd say about 3/4 of teenagers estimate other people's height in feet and inches, and they estimate other people's weight. About a third of them use stones and pounds, even though they've never been taught it at school, which shows how important that bit of maths is, but it has consequences. When I get teenagers to answer this question, and I've done a research, hundreds of teenagers, year 10s in particular, here's Holly's answer to the question. 7'1" and 16 stone she's written. She's probably never had to write stones down before, but that's what she was thinking. I want to point out not those answers, which I think are okay, but what she's done next to them, which is to say, I got that one wrong and I got that one wrong. So this notion of, unless she said exactly what the answer was, 18 stone whatever, then it was the wrong answer. And I fear that's the way she sees any question that's linked with maths, that you've either got it exactly right or you are wrong. And of course, in estimation, we all know there's really good answers, there's not quite so good, and so on. So I'd say, well done, Holly. Those are pretty good guesses. Did anyone get closer? So estimation is just a really useful skill to be practicing, and the reassurance that in this, of all things, ish, the word ish, ISH, is really helpful. It's, that's roughly right is good when it comes to so many numbers in real life. And you can play these kind of, this is just as relevant for your sixth formers as any younger, occasional little quizzes to say, right, I want people to, if you don't know it already, estimate what's the population of the UK, how far is it from London to Edinburgh, what's the weight of a pint of milk. All of these things are handy things to know. And if you're doing what are called Fermi estimations or general estimates, often you do those estimates by comparing them to some rock figure that you know. And these are all useful base levels of knowledge to have, so you can compare other things to them. You might, as you look down that list, all be having your own estimate what you think those figures are. Here are some ish numbers from me that you can debate. 70 million-ish, really useful when hearing how many people have been vaccinated at the moment, how that compares with the total population. World population, likewise, getting towards 8 billion. London to Edinburgh, 350 miles. It's certainly more that than 100 miles, for example. And London to New Zealand, more like 12,000. That's about as far as you can go around the globe. 3 to 4 miles an hour, because that's the speed we tend to use when estimating speeds. Passenger planes, 500 miles an hour. Pint of milk, a pound, half a kilogram-ish. Family car, that's what a ton looks like. And then there's imperial and metric conversions, which, as I mentioned before, this is important because we all go around carrying around these different sense of measurement. And the most basic bit of maths that's so unsexy, it's barely covered in a lot of secondary maths. It's probably more in the sciences than in maths itself. But when your students leave out into the real world, or into the working world, they are going to be faced with measurement all the time, and they might be thinking in one unit, and the person they're dealing with thinks in the other unit. They have to be able to relate to each other. And there are some great ways of doing pretty accurate conversions. Miles to kilometres is approximately 8/5, 1.6. That's very close to the correct answer. Here are some other conversions that you might well need to make, if nothing else, if you're going to America, because they use almost exclusively imperial units there. And there are some approximate conversions. Great if you know those. But here's the skill that I think would be really useful for every school leaver to have, which is the ability to do this roughly. Unfortunately, roughly in this case means double. It's about double, 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 and add 30, double, and just a little twist at the end. Meters and yards, they're basically the same. If everyone left school knowing that little rule of thumb, it will get them a long way. It's a very useful and very little known set of facts, given how important it is, how often it's going to crop up in their lives. So there we go. Wrong answers, but usefully wrong, not too far off answers are really important. And in a way, that's how numbers work in the real world. Numbers we hear on the news aren't the right numbers, they're just approximate numbers. And I think students just need to be reminded that that's the case. The real world is not a maths question. That brings me to part 4, which is surprises. And hopefully you've already had a couple of surprises. I just want to give you already by saying a couple of surprises, you immediately know, well, in that case, I won't be surprised because I know it's a surprise. But even if you know these examples, I suspect your students don't know them. And the first is one of my favourites. Some of you might well have seen me doing this on the circuit over the last 3 or 4 years. It's a sort of half-true story. My local football team, Dulwich Hamlet, made it. I think they were in League 8, what's the equivalent of League 8, and they got promoted to League 7. Maybe it was 7-6. Anyway, they were promoted a couple of seasons ago, and delighted. So the story I like to tell is of the last home fixture. The team are all going to come back to play a home fixture, and the manager thinks, wouldn't it be nice to tie some bunting between the base of the corner flags at both ends of the pitch and lift it up in the middle, and the team will come onto the pitch under the bunting and the crowd will cheer them, and that's all very nice. So the pitch is 100 metres long, and the manager sends the assistant off to the DIY shop, and the assistant comes back with bunting that is 101 metres long. So the manager's just wondering about this and thinking, okay, so how much will they actually be able to get under here? So is it A, that the players will only just be able to get their fingers underneath, or B, the players can crawl underneath, or C, they can get underneath if they crouch, or D, they can comfortably walk underneath? Now, as before with I'm Very Rich, I'm not going to ask you to work this out because the maths will tell you the answer. What's your intuition telling you about this? So we'll do a poll, and those options will be there. Remember, it's 101 metres of flags and 100 metres of pitch. So what is the answer? Is they'll be able to get their fingers underneath, crawl underneath, get underneath if they crouch, or comfortably walk underneath. I'm not going to attempt to guess what the answers will be here, but I am going to guess that the answers will not be the same as you'd get from your class if they are in year 10 through to year 13, which is why I love this problem. Hopefully you've all had a guess, and I've not given you time to work it out, most of you anyway. Let's have a look. Oh, well, okay, beautifully, evenly spread. There is a D has come out the winner, but the other 3 pretty even. Well done if you said D, which we'll come to that in a second. I mean, it's totally plausible why it might be any of the others. You think 101 metres for a 100-metre pitch, there's only a metre spread between all of that length. That doesn't seem to be much slack to go round. Or perhaps you think, well, there will be enough slack by the middle of the pitch. So I can see why A, B and C might get answered, but D is the correct answer. But it's sort of correct, but that's not the end of the story, because, well, what you, I'm sure, spotted here is we have a triangle, 50 metres half the pitch, and 50.5, that's half of the length of the bunting. We want to know the height. Hey, we've got a real world Pythagoras problem. How much have people been desperate to see one of those? And here are the numbers, so you don't have to work them out yourselves. We want to know question mark, and you plug it into a calculator or do it in your head or whatever. 50.25, square root of that, 7.1 meters. So not only can the team comfortably walk under the bunting, but they could actually get onto the team bus, stand up on the top deck of the double-decker bus, and still comfortably get underneath, which is like, wow. It's not just that D was right, but D was, I could have put a fifth option, which would have seemed extraordinary. So I love it that even Pythagoras could throw a surprise, and just goes to show, never take any bit of maths for granted, unless you saw that straight away, in which case you will not be surprised at all. And let me give us my last example. Actually, I'm not going to give you a black queen. I'm going to give you Pascal's triangle, because it's very relevant, especially if your year 12s and 13s have just encountered this. A quick reminder of Pascal's triangle and how you might remind them of it. That the lovely notion that each row is made by putting ones on both ends, and then each number in the middle of each row is found by adding the two numbers above left and above right. So 1, 3, 3, 1. The next row is going to be 1, 4, 6, 4, 1. Always adding the two numbers above, and so on. There's 10 rows, and there's lots of lovely patterns buried within Pascal's triangle. I love the fact that the rows add up to the powers of 2, 1, 2, 4, 8, 16. How did it know to be able to do that? So beautiful. For example, that diagonal sort of is 1, 3, 6, 10. Those are the triangular or snooker ball numbers, as I sometimes like to call them. But actually, I'm going to point you to something a little bit more mundane, which is that some of the numbers in Pascal's triangle are odd, and some of them are even. Now, I'm just going to give you a bit more of Pascal's triangle. There's 14 rows, but now I want you to imagine 1,000,000 rows of Pascal's triangle. So it's a really massive Pascal triangle, and lots of patterns have begun to emerge or whatever. And I'm just going to ask you to have a guess, and if you know the answer already, don't put the answer in the chat box again. Just sit and feeling very happy that you already know this. But it turns out that the proportion of numbers that are odd in Pascal's triangle tends towards a particular number. So to the nearest percent, what percent of the numbers in 1,000,000 row Pascal's triangle will be odd? Will it be 67% or 50%, 33%, 25%, or 0%? So use your skill, judgment, and guesswork to pick A, B, C, D, or E, and I will pop through to the poll now. Just give you a bit more time to just inspect. It's very hard to see some of those small numbers, especially if your broadband's not great at home, but hopefully you can sort of get a sense of what those numbers are. There's a tiny 716 somewhere in the middle of that penultimate row. Okay, so A, B, C, D, or E. Again, I'm not going to try and guess what proportion you're going to go for, but I suspect you're not all going to pick the same value here. I can't even remember which one tends to be the most popular pick, but of course somebody is going to get it wrong. I can guarantee that, and maybe a lot of people will get it wrong, and there's no shame in that. So I hope that most of you have now had a chance to vote on that. There is no chance, of course, to have counted up how many rows there are in Pascal triangle. Okay, well, we have 27%. Looks like the first two, 67 and 50, are winning there, and then it's actually gone in order. 22.5. 17% have gone for 25%, and then 5% bold people have said 0%. Okay, well, good news. Someone has got it right. Before I go back to Pascal's triangle, just a little aside, which is I like to show this to students about a triangular painted wall. I've painted it red with red paint, and I've around the perimeter I've drawn a chalk perimeter. Okay, so but I've decided, you know what, I don't want to paint all of that wall. I'm going to take out a quarter of it. I'm going to take out that equilateral triangle, so I only have to paint 3 triangles, but I am going to have to draw a perimeter around that inner black triangle. So what's happened to the area? It's now 3/4 of what it was. What's happened to the perimeter? You count up, there's 6 green lines there. We've added 3 more, so it's gone from 6 to 9. So we've multiplied the perimeter by 3/2. But let's do the same again. Let's take out a quarter of what was left, and the area is now 3/4 of 3/4, and the perimeter, trust me, has gone up by 1.5, and this continues. So we take away more and more paint, so we're needing less and less paint, and where this is tending to is, in the end, we're going to end up with a triangle where we don't need any red paint at all, but unfortunately we are going to need, oh, that 8 has rotated, that's a font thing, that should be infinite, not 8. There's a mistake for you, but that's PowerPoint playing games. Anyway, infinite perimeter and no area. What a wonderful shape. What a wonderful notion. And this is known as Sierpinski's gasket. The main point is no red paint. Now, let's go back to Pascal's triangle and let's paint it red. So I've just painted Pascal's triangle red, and let's blur our eyes or in a moment. First of all, let's look for the even numbers. There's a 2, and there's more even numbers. I'll put a triangle around those, and more. It's interesting because they make these interesting triangular shapes. And I'm going to take out all the even numbers, and now you can blur your eyes and imagine those odd numbers turning into red blotches. And now let's just move outwards. And as we move outwards, you can see that Pascal's triangle becomes Sierpinski's gasket. And there's one thing we now know about the amount of paint you need on Sierpinski's gasket, which is you don't need any paint, and paint is odd numbers. So in Pascal's triangle with 1,000,000 rows to the nearest percent, the answer was E0%. Well done to the 5% of you who stuck your necks out and said the unpopular answer. And the rest of you might well be saying, but hang on a sec, it can't be 0, because look at all those 1s, and there's going to be 1,000,000 of those on either side if I paint those pink. And there's loads of other odd numbers too. And that's true. And you go to an infinite, Pascal's triangle will be an infinite number of 1s, but a different level of infinity of even numbers. And actually the pattern, is a bit deceptive in this. You can actually estimate or work out using a model with some quite tricky maths on it. 2n to the 0.586, does that say, divided by n plus 1? It's got a missing line in it. But anyway, there is an estimate of this, which allows you to say what proportion of numbers are going to be odd as you increase the number of rows. So with 1 row, the number 1, all of the numbers are odd. By the time you get to 10, which is roughly what you were seeing in my first illustration, still the majority are odd, which is why 67% seemed a decent guess. But by the time you get to 100, it's only 30%, and the numbers go down and down till it's about 0.2%. Actually, you'd really need to go to 1 billion for it to be closer to 0 than 1%, but it's pretty tiny, even at 1 million. So there you go. Surprising, interesting, and isn't this the kind of really interesting maths that got you all into the subject in the first place? It's only the kind of stuff that intrigued me. And invariably, it's stuff that I got wrong, is the stuff I like the most, because it was surprising. And maths should be surprising, and unfortunately so much curriculum stuff is not surprising, and the whole idea of exams is not to surprise you too much, because that's not what's being tested. So just as a sort of recap, mistakes happen. Mistakes are part of problem solving. There isn't always a right answer, and getting it wrong can be interesting. So, no one wants to be getting things wrong, but there are lots of good reasons to get it wrong, and to create an environment where you can get it wrong and not feel like you're a failure or being made fun of or whatever. And just to go back to a point I made earlier about getting participation, that's so important. When we're doing maths inspiration shows, it's vital we get volunteers on stage. And there's a little saying, the volunteer who gets things wrong often makes the biggest contribution to understanding and problem solving. And you're wondering, who said this? Where can I find this quote? The answer is I said it about 20 seconds ago. So it doesn't have to be Einstein who makes quotes. We can all make up our own quotes, stick a name at the bottom. If you believe that, then take it away. And if you don't believe it, just forget it. But I hope that has given you some thought-provoking things about making mistakes and getting it wrong, and where that can prove to be useful in the classroom and in some of the enrichment that you give to your students.